thank you, for coming to this defense. Just would like to introduce, Kenneth Allen. He is going to defend his master thesis within our master program in applied physics. And Ken basically joined my lab, studying from attending group meetings in winter of 2009, and he was an undergraduate student in my lab for several years, and I'm proud to say he was NSF research experience undergraduate within NSF supported in summer. There is a special framework from NSF to support working for undergraduate students for several years, actually for 2-3 years. And last year he's a full-scale graduate student in my lab. So he's presenting kind of work accomplished over some period. And our plan for today is to have this presentation by Kenneth for maybe close to half an hour, maybe 35 minutes. And then you are expected to ask questions. So I would like to encourage you to ask anything you like. And questions can be of various nature, kind of, you can ask about the subject and about, all types of issues related to this defense. And there is lots of adverts, and this is supposed to be a public event. So which means that you are supposed to come here to ask questions, and kind of find out what he really did. Okay, and you know the procedure, so after that, the committee members, we will have a discussion about this defense. So once we finish this open, session, I will have to ask, you to leave the room because we need to have some more thorough discussion based on reading of this thesis, and if it's well, we'll have to leave the room. Okay, and after that, you will wait, and we will tell the results.
My defense is on light focusing and transport properties of mesophotic structures. The structures which are studied in this work are in the mesophotic regime. So when the size of the sphere is much greater than the wavelength of light, sometimes it's best to model these with the geometrical optics model, looking at it from a ray point of view. And then when the sphere diameter is on the order of wavelength scale, it exhibits features which are of wave optics, so I'll call that physical optics. So to be a little bit more rigorous, when the sphere diameter is greater than 20 times the wavelength of incident light, I'll call that geometrical optics. And then when it's a wavelength scale sphere, I'll call that physical optics. I would like to give you a little bit of background introduction, just in this field in general, and then some fabrication techniques which were used to make these structures, then go over a couple of experimental techniques that I use to optically characterize these structures, followed by a chapter in my thesis on microsphere arrays integrated into microcapillaries, followed by a chapter on focusing and transport of optical beams in chains of spheres spanning physical and geometrical optics, and then brief conclusion. There are two types of optical transport mechanisms in chains of microspheres. One of them that are based off of the resonant properties of the microspheres, one of them that is based off of the non-resonant properties of the microsphere. For the most part, the work that I did was focus on the non-resonant properties of these chains of microspheres. However, I feel that it's necessary to briefly mention the resonant properties just to get a complete background. So the light waves can be trapped inside of cavities which have circular symmetry through total internal reflection. And if this light wave through one round trip inside of the cavity is in phase with itself, it constructively interferes, and this is a resonant frequency of that cavity. If you bring another resonator within close enough proximity, you can couple the light from its evanescent field into the other cavity and transport the light. Now for some of the non-resonant effects. So classically, focusing of a single spherical lens is well understood. In this work, I present spheres, which is just a special case of a thick lens. And if you have a well-collimated source, you can get a diffraction-limited spot size. However, recently, there has been some study for near-field phenomena that it doesn't really fit that classical model very well. And this is under two conditions. One is if the refractive index contrast of the sphere is roughly 1.6 times greater than the background medium. And then also if the spherical lens is on the order of the wavelength of light, which is incident onto the sphere. If you take a case of just a plane wave incident, you will have a narrow optical beam emerge on the back surface of the sphere. This beam, its peak intensity will be 3 orders of magnitude greater than the illuminating wave. It'll also have a full width half maximum as small as a third of the incident wavelength of light, which is smaller than the classical diffraction limit. And then also the waste of this optical beam will propagate for on the order of 2 or 3 wavelengths without experiencing much divergence. Both of the cases I just mentioned were only for plane wave incident or a well-collimated light source. If you consider a multimodal light source, as shown here, if we look at a chain of microspheres with a locally integrated source of light, such as a fluorescent diode sphere here. Once this diode sphere is pumped by a mercury lamp, it will isotropically emit light in all directions. And then all these Maradno and skew rays will be focused along the backside of the surface of the first sphere. The overlapping of these different rays focus will correspond to a broad spot size, which is here. So you don't get the same small spot size after one sphere. However, as the light propagates through the chain of microspheres, you will filter out some of these higher order Maradno and skew rays, which corresponds to successive focusing of the optical beam's waves as it goes through the chain of spheres. And this successive focusing effect I will call beam tapering. Previously in the mesophotonics lab of Dr. Ashton, it has been observed that you have this successive focusing of the optical beam in chains of microspheres that are wavelength scale spheres. Also, at distant portions of the chain, away from the source sphere, they have experienced very low attenuation, approximately 0.08 dB per sphere. These results have really motivated and guided my work because although these effects have been studied, they haven't been studied in great detail, such as these optical properties. How do they depend on the diameter of the sphere size comprising these chains? And then also, because of the focusing properties and attenuation, maybe some of these devices could be used for multimodal focusing microprobes. So in order to study these structures, first they have to be fabricated, which isn't trivial because some of the sphere diameters are as small as 2 microns. So in order to do this, I use a self-assembly technique, which involved having the spheres in liquid suspension wedged between 2 substrates. And then as this liquid dries, you have an evaporation front, which, as you can see here, and then there's a flux of spheres, which is just being gradually pulled along this flux. If there's any sort of defect on the substrate, some of these spheres can get caught inside of this defect. And then the evaporation wavefront will continue to move past this defect, giving you a long liquid channel. And the sides of this liquid channel are still subject to evaporation, so it will continue to get thinner. And then the flux of spheres will continue to move due to microfluidic forces into this liquid channel, creating long straight chains up to 100 spheres long with minimal deviations. After these long straight chains of spheres have been assembled, you still need to insert locally integrate your source of light. So that was done by micro manipulation techniques, using a hydro micro manipulator, which had a tapered metallic probe attached to it, or a tapered fiber, which allows you to controllably place your source sphere into the chain of spheres at a desired length. And these spheres in this image are 5 micron diameter. So after you fabricate a long straight chain and you have a locally integrated source of light, you still need to optically characterize these structures. There was 2 methods of optical characterization. One of the methods was to optically characterize this structure by examining the light that is scattered perpendicular to the axis of propagation of the light. And then the other experimental technique is to directly collect the light along the axis of propagation. Okay, so imaging using the scattered light technique. This offers, it's advantageous because it allows you to capture several intensity profiles in a single image versus direct imaging where you can only get 1 profile per image. And here's the experimental setup that we used to do this imaging by scattered light. So we have a mercury lamp, which is our pump, and then we have a spectral filter, which only allows the excitation wavelength to come through. The excitation wavelength goes through the objective, excites the fluorescent diode sphere, and then it re-emits light, and a small portion of that light is coupled into the chain, and then at the interface between spheres, the light is scattered and then collected by the objective, passes through a spectral filter so you don't see the excitation